Let's say we wanted to evaluate our trigonometric functions at a specific location, say pi or basically anywhere. Uh, Going back to the definitions, what was critical about being able to evaluate it is to know the correspondence between t and the point itself. Because in order to solve it, it says that the sine of t is defined to be y. I need to know both the t, the location based on the terminal distance like pi over 2 or whatever, and I also need to know, well, what's the associated y value, where cosine is the x and each other one is a various ratio. So say, for example, I wanted to evaluate the sine of pi. What that's asking, or what that's kind of getting at, is this is going to be a t value. This is going to be the position based on distance from the initial to terminal point. And that's a point we considered earlier when we were developing, trying to dis discuss the points on the unit circle and why they exist. But basically, since that's half a circle, we know the full circle is 2 pi, half a circle is pi. Therefore, if we go pi around the unit circle, we will wind up at the terminal point -1 comma 0. So since we know all that, we know how to evaluate sine of pi, because sine of t always is equal to y. So what sine will return is the y value at the coordinate at that specific location, aka 0. Whereas cosine returns x. Each one, sine and cosine, returns one or the other. How you can always remember it is cosine is always the x, sine is always the y. Those are the two easiest because they're just directly uh, given by the unit circle. So let's go to the whiteboard so I can, we can fill some of these in. But essentially, the sine of pi is going to be equal to the y value at that location. Since I know the location and I know the respective terminal point, sine of pi must be equal to 0. And similarly, since cosine of t always returns x, cosine will give me the x value at that location, aka -1, and I will get exactly that. Um, and that's the gist of how we evaluate trigonometric functions. It's sort of like, well, the natural log of, 1 or whatever. We're evaluating by plugging it in. It's a little bit of a more complicated process than just doing some algebra, uh, because it's not necessarily an algebraic process. It's the way the functions work are all based on the unit circle. So anytime we're trying to figure something out, we always got to think about the unit circle as the origin of the relationship. Now the other four trigonometric functions are all ratios of x and y. Tangent is always going to return the ratio of y to x. And again, what I recommend is when you're first, if you're not too familiar with them, start with the definitions that I had shown you and that's on the packet, and just kind of use them to practice getting started. But tangent is always y over x, so in this case it's going to be 0 over -1, which is of course 0, and so on. And the other three functions, secant, cosecant, and cotangent, um, let's go ahead and just bring it back up to review. But sine is always y, cosine is always x, tangent is always the ratio of y to x. Notice that cotangent is the reciprocal to tangent, it's the reverse. And secant and cosecant are the reciprocals to cosine and sine, respectively. So if I want to evaluate cosecant, I take 1 divided by y, secant is 1 divided. So using that information, let's just do, say, secant first. Secant is reciprocal to cosine. It's 1 over x, 1 over 0, because, sorry, that x is not 0. X is -1 at that location. But secant of pi would give me 1 over -1, which is, of course, -1 as well. Go ahead and circle my answers here. Then we have the other two, which are cosecant, cosecant of pi. Cosecant of t is always going to be 1 over y. It's reciprocal to sine. So since y is 0, that would give me 1 over 0. Now, of course, you can't divide by 0. That's a rule in math that we've discussed already. We reviewed this before in the semester. But another important thing about trigonometric functions, they're not always defined. They have domain problems. Well, specifically, since 4 of them involve division, those ones are naturally going to have problems at certain locations. And what actually happens is, like with rational functions that we studied back in chapter 3, it's going to end up creating a vertical asymptote in the graph, just like how when we had a polynomial like this, right? We got a vertical asymptote at 3 because it caused like as I described it, caused the graph to explode when we divide by 0. But similar things happen with trigonometric functions that involve division. But notice the sine and cosine don't involve division. Those ones don't have problems. It's the other four that have their problems. Anyways, it's undefined, so we would say that pi is not within the domain of the cosecant function. So, it's kind of like invalid, uh, and it's would have a vertical asymptote at that location. And same exact thing with tangent, or sorry, not tangent, cotangent. Um, we already did tangent. Cotangent of pi is defined to be x over y. So x is minus 1, y is 0. Again, an undefined ratio because we cannot divide by 0 fundamentally. And so another issue with this. But notice at the end of the day, we can evaluate our trigonometric functions assuming we're not dividing by 0, and we're good to go. And actually, if you go back and pay attention to the fine print, um, notice that it actually has it built into the definition. It says, well, cotangent of t is defined to be x over y, assuming that y is not 0. So in those cases, cotangent's not really defined to begin with. So we're just not, it's kind of like we're not allowed to use pi uh, in those examples because it just doesn't work. Or we would just say that it's not within the domain of the function.